Hey everyone, welcome to my channel. I am Khan Madam and I am a lecturer by profession with the passion of teaching. Join me on this channel, Physics by Khan Madam, for a relaxed and supportive learning environment where we explore physics as a subject together. Before we start, I would like to inform you that we are starting from the basics of physics and we will gradually and steadily move forward to more complex topics as well. These lecture series specifically will be more helpful for the students undergoing graduation in physics under NEP, which is New Education Policy. Okay, let's start with our lecture series. First and foremost, let us discuss the topic that we will be studying. We have the simple harmonic motion part 1 as a unit name. Under this we have oscillatory and simple harmonic motion, differential equation of SHM and its solution, velocity and acceleration of simple harmonic oscillator, graphical representation of displacement, velocity and acceleration, period and frequency of SHM, energy of SHM, and example of SHM. Example of SHM includes spring mass system, simple pendulum, compound pendulum, torsion pendulum, and few salt examples. Okay, before we jump directly to the topic, let us have a brainstorming session together. First situation is that think about a swing. A swing goes back and forth, right? But if you give a bigger push, does it swing faster or go higher? Okay, imagine a second situation where you assume a clock pendulum. Which type of motion does it exhibit? In both the above cases, your object is moving to and fro about a center position or point. This kind of motion is known as oscillatory motion. In everyday life, we came across numerous things that moves. These motion are of two types. Either the body moves about a mean position or the body moves from one point to another. The first kind of motion in which the body moves about a mean position is known as a oscillatory motion. As you can see here, a simple pendulum have a bob, and this particular motion, if you consider this bob and you take this bob to its extreme position, it will oscillate about its mean position or equilibrium position. This kind of motion will be an example of oscillatory motion. Another kind of example or the motion that is exhibited in our day-to-day life is a motion of a body from one point to another. So this kind of motion can be seen where a car or an object moves from point A to point B. Sometimes both the phenomena is exhibited at the same time. For instance, example, motion of a sea wave. Like wave appear to be traveling towards the beach as the motion from one point to another, but it also moves up and down about the mean position. Thus, we can say that oscillatory motion is a broader term, or it is a kind of motion which repeats itself. Its restoring force can be of any form. Its path can be linear, circular, or any shape, and its acceleration is not necessarily proportional to the displacement. Right? Oscillatory motion is an umbrella term or broad term, but one specific type of motion that we are concerned for our studies is harmonic motion, or more specifically simple harmonic motion. If we talk about simple harmonic motion, it is a specific type of oscillatory motion, okay, with linear restoring force proportional to the displacement. Okay, what is restoring force? It is a kind of force which which actually grabs the body to its mean position. The proportional displacement, it is in simple harmonic motion, restoring force is proportional to displacement and acts in opposite direction. In SHM, path is always linear, and in SHM, acceleration is directly proportional to displacement and acts in opposite direction. Now we will study more specifically about the simple harmonic motion. Imagine a bob tied with a string. Okay, a bob tied with a string along a strong surface. Now imagine a simple bob tied with a string and its complete assembly make a structure of simple pendulum. Okay, if you pull the bob at one extreme and release it, you'll notice few things. What are these few things? The bob will move faster when it will come towards the mean position. Second, the speed will be maximum at the mean position. Third, the bob cannot reach further after certain point or certain limit, and this complete system or complete motion will gradually ends after certain time. So in scientific language we use the term equilibrium position or mean position, where your bob rests. These are the same thing I have mentioned here. These are the same things that I have mentioned here. If you have a question, if you got a question in examination, what is simple harmonic motion, so you have to draw this particular diagram and explain it in words like the velocity of vibrating particle is maximum at mean position of rest and 0 at maximum position of vibration, right? And the acceleration of vibrating particle is 0 at mean position and maximum position of maximum position of vibration. The acceleration is always directed towards the mean position of rest, and it's directly proportional to the displacement of vibrating particle. This type of motion where acceleration is directed towards a fixed point, that is mean position, and is proportional to the displacement of vibrating particle, is called simple harmonic motion. So these kind of motion is known as a simple harmonic motion. You can consider this as an example of simple harmonic motion, or you can consider this is also a kind of simple harmonic motion where this particular area is a rigid support which is added with a spring and a mass. So this complete assembly known as a spring mass system. So this is a complete example of spring mass system. Up till now what we have done, we have studied the theoretical concept of simple harmonic motion. Now we will see how one can represent the relationship between linear acceleration and linear displacement by mathematical expression. Before that, first look at this picture. This makes the same assembly as we have discussed a couple of seconds ago. A rigid support attached with a spring and spring attached with a mass. In the first figure, a mass is attached with a rigid support on a frictionless surface and it represents the equilibrium position. No force is acting on this particular mass. In the second diagram, we have pushed this mass towards the rigid support. So we are applying force in this direction, but the restoring force will be acting on in a opposite direction. Okay, in the second diagram, we have pushed the mass towards the rigid support, hence restoring force will act opposite to the applied force. And in the third diagram, due to restoring force, the spring will expand and this time restoring force will be towards the rigid supports. Since in both the cases the restoring force in opposite direction to applied force, that is displacement, we can represent it as this force is directly proportional to displacement, but this negative sign shows that it is in opposite direction. Okay, let us keep this an equation number 1, or before that you'll add this kind of theory in explaining. Consider one end of a spring is fixed with a rigid support and to another end of spring of a body of mass m attached, which is free to move over a frictionless horizontal surface. When the body is displaced towards left, the equilibrium position, the force exerted by a spring on the body, it's towards the right. Basically it is in opposite direction. When the body m is displaced towards right from the equilibrium position, the force F exerted by a spring on a body is directed towards left. In both the cases, the force F is restoring force. We have considered X as a displacement and F is applied force. So this is how we have F equals to minus X. Now we will remove this proportionality sign and we will add proportionality constant, which is a force constant. So now we have F, which is force, is equals to minus Kx. Negative sign shows that the force and displacement are opposite directed. Now we know that the second law of Newton, which is given by F is equal to ma, force equals to mass into acceleration. If we want to deduce the value of acceleration, we can simply put m underneath F. So we will have the acceleration of a body is given by a equals to F by m. Now from the first equation we have studied here, from the equation A, we know that f is equals to minus kx. We have substituted f equals to minus kx by m, and we know that angular frequency of body is given by k by m. Omega square equals to k by m. So we will put k by m as omega square and this negative sign as it is. Now here a is a linear acceleration and x is a linear displacement. So we can say that linear harmonic motion is defined as a linear periodic motion of a body in which restoring force acceleration is always directed towards the mean position and its magnitude is directly proportional to the linear displacement from the mean position. So here we have mathematically proved that our linear acceleration is directly proportional to the linear displacement. Hope you have understood the concept of oscillatory motion. Simple harmonic motion. Here we have studied the basic difference between oscillatory motion and simple harmonic motion, and you may have studied about the the mathematical relation between linear acceleration and linear displacement. In upcoming lecture we will study about differential equation of linear harmonic motion and its solution. Till then, keep studying. Bye bye, take care, see ya.